All right, this is Honors Algebra 2 Pre-Calculus. We're doing 8.2 in Algebra 2. This is our second video in this series, and we're talking about horizontal asymptotes, slant asymptotes, and Y-intercept. So what are horizontal asymptotes? So we've seen these before. In Chapter 6, we saw this with exponential graphs. Essentially, they're the end behavior of a function for a very large positive or very large negative, meaning approaching infinity or negative infinity value of x. So graphs behave like that asymptote for those huge values. So we've seen y equals e to the x from Chapter 6. So this graph has a horizontal asymptote of y equals 0 on one side. See how this red graph is approaching y equals 0 on the left side as x approaches negative infinity. Now, as x approaches positive infinity, meaning going this way, this thing's going up forever. So you can see that the limit as x approaches infinity, meaning as you go as far to the right as you possibly can, right? And the reason we use that word limit is something we're going to see in calculus, but basically it means approaching a value you cannot mathematically reach. As you go infinitely far to the right, the e to the x goes all the way up, meaning goes up to an infinitely large value, right? So the fancy math notation for the other direction is as you go as far to the left as you possibly can, right? As x approaches negative infinity, e to the x has an output of 0, right? It's approaching 0, but it's not actually 0. So anyway, we've seen horizontal asymptotes before. So here are some graphs with horizontal and slant asymptotes just to give you a basic idea of what these things look like. So we're mostly going to be doing graphs like this. So the red is the curve, right? So the red is this curve, right, that we're looking at. See how that's in red, right? And this blue is the horizontal asymptote, okay, in blue. Sorry, I should probably put a blue pen for that reason. So the blue is the horizontal asymptote. Just a point of clarity, if you were having any trouble with what vertical asymptotes are, this green thing here, that's the vertical asymptote from the last video. So a vertical asymptote is like a vertical fence in a graph, right? Not every graph has a vertical asymptote. This one does, right? That's the vertical asymptote. So these blue things, this blue thing right here is a horizontal asymptote. See how the red curve, if you trace this red curve, you can see how as x gets really, really far to the right, you see how the graph behaves like the blue line. And as x goes really, 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 really far to the left, this red graph behaves like the blue line, right? Here, right, here's another example of a horizontal asymptote. The graph does other stuff in the middle, but for really big values of x in either direction, really big negative or really big positive, the graph behaves like the blue line, okay? That's essentially what it means to be a horizontal asymptote. So you won't likely see any like this now, but I just want to throw this out there as a thing that can happen, right? In calc, we'll see this sometimes. Some graphs actually have two different horizontal asymptotes. See how this one follows this blue line, right? Y equals 4. And this one on this side, this other branch, follows this blue line of y equals negative 4, right? So if we were talking fancy math notation, the math notation would be that the limit as x approaches infinity, meaning all the way to the right, of this function f of x is a 4, right? Because as you go all the way to the right, it behaves like y equals 4. And the limit as x approaches negative infinity, meaning all the way to the left, this way, of this function, well, it behaves like a negative 4, right? That would be the fancy math notation that you don't have to know yet, but we're going to address when you get to calculus next year. So moving on. Okay, so this is what a slant asymptote looks like. It's named slant because it slants. Essentially, when you have a function where this degree is 1 higher than this degree, and we're going to spend some time figuring that out in the next couple slides, what you end up with is this kind of blue line that is essentially a linear equation, and the graph follows that linear equation. So see how for very large values of x in either direction, as you go as far to the right as you can or as far to the left as you can, the red curve behaves like the blue line. So this is my function, and this is my slant asymptote, right? So we're going to go over how to find that on the next slide, but I just want to show you that that's what a slant asymptote looks like. We're not going to see a ton of them, but that's how it works. All right, so let's walk through how you find the y-intercept or y-intercept and horizontal or slant asymptotes. All of these use standard forms. So these are going to use this form, not the other two forms, okay? So we use the factored form for the last one. We're going to use the standard form. So essentially, so the y-intercept is pretty straightforward. Basically, you're just going to plug in x is 0 and see what y value you get out. If you get a resulting y value, like let's say you get a 3/5 or a 2 or a 7, that's your y-intercept, that's great. If you get 0 over 0, you don't have a y-intercept. What you have there is a hole, right? And we're going to talk about that when you know, if you go back to the last video about finding holes, what that's going to mean is that you have a hole, and then once we, so that goes back to the last video, but we'll address that more when we start actually graphing in the third video in this section, okay? So for horizontal asymptotes, when we look at horizontal asymptotes, and I touched briefly on this a second ago, but basically the horizontal asymptotes are all about the degree of the numerator and the degree of the denominator, which I'm going to call n and d. If the degree of the numerator is smaller than the degree of the denominator, so here they're the same, but let's go ahead and walk through a couple examples. So if this thing, we'll call this case 1, case 2, and case 3, right? In case 1, if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is 0. So here's an example of that. If the top is an x squared plus 3x, and the bottom is a 5x cubed minus 7x plus 8, the degree of the numerator is a 2, the degree of the denominator is a 3. Since 2 is smaller than 3, the horizontal asymptote is just y equals 0. It's not horizontal asymptote equals 0, it's y equals 0. It needs to be the equation of a horizontal line. So the horizontal line has the equation y equals. The second case is if n is equal to d. Well, that's actually the same case as the one that we're looking at right here at the top, right? This is this situation, right? We have an x squared minus 7x plus 12 over an x squared minus 9. Well, the degrees are the same. Then you're just looking at the fraction of the leading coefficients. So let's go ahead and make up a different one. Let's say I have a 2x squared plus 3x over 5x squared minus 7x plus 3. Great. Since these are the same degree, my horizontal asymptote is just the fraction of the leading coefficients. So since 2 is the same as 2, the two powers are the same, my horizontal asymptote is just y equals 2/5. Right? And so that's what it says here. It says lead coefficient over lead coefficient. Now, the last case, if n is bigger than d, there is no horizontal asymptote. So let's say we have x to the 4th plus 7x over x plus 8. This is a 4, this is a 1. So 4 is bigger than 1. There is no horizontal asymptote. This graph is going up or down to infinity forever. However, if you have the rare case where the numerator is exactly 1 higher than the denominator, then you're going to have what's called a slant asymptote. So I want to go back to this one. See how this numerator had a degree 1 higher than the denominator? Then we got what's called a slant asymptote. And the way we find that slant asymptote is we find the quotient, just the quotient, not the remainder over the divisor, and that's my slant asymptote. So I divide, but that only happens if the numerator degree, just like we saw here, is 1 higher than the denominator degree. All right, so moving on, let's go ahead and walk through this. We're going to find the y-intercept and horizontal or slant asymptotes. So again, you don't need to factor for this, right? So for the y-intercept, I'm just going to plug in x is 0 and see what happens. So I get y equals 0 plus 0 plus 2 over 0 minus 18. So I get a negative 1/9. That's it. That's my y-intercept. My y-intercept is negative 1/9. And then for the horizontal asymptote, I just look at the degrees. I see that they're the same, and I say, oh, that means that I just need the fraction of the leading coefficients, and that's it. There is no slant asymptote. So a thing to notice is you don't have both a slant and a horizontal asymptote. So you either have a horizontal asymptote or you have a slant asymptote. You don't have both. All right, let's go ahead. All right, so same idea. Give this a try. You're going to find the y-intercept and the horizontal or slant asymptote of this rational function. All right, so you can pause me if you're ready to do it on your own. So when I plug in x is 0, I get y equals 0 minus 10 over 0 plus 0 plus 5. I seem to get a negative 10/5, which means my y-intercept is a negative 2. For my horizontal asymptote, I notice that this degree is 1 and it is smaller than 2, right? So since the top degree is smaller, my horizontal asymptote is just y equals 0. There's not really much work to show there. All right, so we're going to find the y-intercept and then the horizontal or slant asymptote. So let's start with the y-intercept, which means x is 0. And I think you're probably catching on that if you notice, when I plug in x is 0, all of those x's go away. So if you're able to plug that in your head and just get the 1/2 ahead of time, that's definitely not cheating. If you need to plug this in like this, also totally not cheating. Don't care, whatever you want to do. So I get y is 1/2. Now, this one's going to be a little bit trickier for the horizontal asymptote. Because the numerator degree is bigger than the denominator, there's none. Okay, there is not a horizontal asymptote. But to make matters more complicated, because the numerator is 1 bigger, there is a slant asymptote, right? And some graphs don't have either of them. Some graphs don't have a horizontal asymptote or a slant asymptote. In fact, if you go back to this example, This one had no horizontal asymptote, and because 4 is more than 1 bigger than 1, there's also no slant asymptote. Some graphs have neither, but this one has a slant asymptote. So to find the slant asymptote, I need to divide. And you're not going to see a ton of problems with slant asymptotes, but there are problems that have them, so we're going to make sure we get the concept. So if you recall the way long division works, and I should use long division here because using synthetic division is difficult when you have a nonlinear divisor. Not impossible, but just not really worth it. So I'm going to make the leading term of this polynomial look like the leading term of this polynomial. To do that, I would have to multiply by an x, and then I distribute the x to everybody that's in the car, right? So x cubed minus x squared plus 2x, and then subtract straight down. So the x cubes are going to go away, which is totally what should happen. X squared minus a negative x squared will become a 2x squared, right? X minus a 2x is a negative x, and then I drop the 1 straight down. I want to make this leading term look like this leading term, so that's going to be a plus 2. So I get 2x squared minus 2x plus 4. And then subtract straight down. The 2x squareds go away. Negative x plus a 2x is going to be an x. 1 minus a 4 is a negative 3. So this is my remainder, but I don't really care about this. I care about this. My slant asymptote is the quotient. So my slant asymptote is y equals x plus 2. Right? So I don't care about the remainder. I don't care about anything else. I just care about the quotient for the slant asymptote. All right, go ahead and give that a try. So for P4, you're going to do the same exact thing. I would suggest that you start with the y-intercept because it's easier. So the y-intercept, which is when x is 0, is going to be y equals 0 plus 0 plus 5 over 0 minus 2. I get y is negative 5 halves. Now, when I go to do the horizontal asymptote, I should notice pretty quickly that there is no horizontal asymptote, right? There's no horizontal asymptote because the numerator degree is higher than the denominator degree. Now, when I go to find the slant asymptote, this time you could use synthetic if you wanted because this is a linear divisor. So if you want to use synthetic, you certainly could, and it would be arguably a lot faster. When you have the choice to use synthetic, I would advocate for doing so. Multiply, add straight down, multiply, add straight down. This is my remainder, my number, and my x. So this right here gives me my slant asymptote. It is y equals x plus 5. And you could have done that with long division as well, but certainly easier with synthetic if you have the option. All right, and I think that's the end of that video.